Perfect. So yeah, hi everyone. Thanks for making the time on a Friday afternoon, evening, depending on where you are, to join this webinar series hosted by 12 Labs. So we call it Multimodal Weekly because a lot of our focus has been on multimodal content since the inception. We've been meeting on a weekly basis, the committee here, and here are some of the topics that we tend to cover on a weekly basis. Obviously, we have researchers come and talk about their work in multimodal AI and foundation models, but on other occasions, we also have developers, entrepreneurs come and talk about different application of multimodal AI in different verticals. There's specific projects and tutorials and guidelines from our internal team member come in and talk about. Recently, we right before the break, we have a bunch of folks from our internal team come here to talk about using our tools and technology. But like for the first session of 2025, I kind of want to go back to the research community and invite speakers who've been doing great work on this topic. So all the speakers that you see here on the list are presenters from the NeurIPS conference just last month, and some of them was actually part of our workshop. Some of them have very interesting work in video content that I couldn't resist to invite them. Yeah, quick introduction about the speakers. The first one is going to be Jieyu Zhang and Yiqi Zhong, both a PhD student at University of Washington. So they will give a brief talk about their work called Task Me Anything, which is a multimodal benchmarking generation engine, right? That can generate new benchmark on a different type of task. The second presenters will be Yiqi Zhong, currently a senior researcher at Microsoft, and her work is called Motion Graph Unleashed, a novel approach to video prediction that can, I believe, predict new video frames depending on the input. And finally, we will conclude the webinar with Musha, currently a final year PhD student at University of Wisconsin, Madison. And Mu actually is a second-time speaker. He gave a talk at our webinar in the past, I believe it's in May or June of last year, so it's been a while. But yeah, I think he continuously doing great work in this domain of multimodal video understanding. And today he will give an in-depth talk that covers 3 of the his recent work. 2 of them focus on benchmarking, and the third one is around a novel approach called Matryosha multimodal models. So yeah, that's a brief introduction about the speakers. It's just a quick logistical format for the attendees. Feel free to send your question on the Zoom chat, and then I will surface them into the speaker. And then after each of the session from the presenters, we'll have a short Q&A for the attendees to ask any question, do any interactive real-time question answering. Yeah. So with that, I will stop sharing my screen, and I will unmute Zishan and Jieyu, so you guys can go ahead with the first speaking slot. Yeah.
Hi, everyone, can you guys see my screen?
It's loading.
It's loading.
Okay, now, yeah, go ahead.
Yeah, so today I'm gonna present our works published and last is NeurIPS about it's titled Task Me Anything, and it's about how we generate benchmarks for like multimodal language models. So let's talk about the motivation first. So nowadays we have so many different like multimodal language models, and then at the same time we also have a lot of benchmarks we can use to like evaluate these multimodal language models on. But the question now becomes like, since we have so many benchmarks, and which benchmark should we use like to evaluate a certain perspective of the model we care about? So in this work, we try to, and also given all these models, which model we should use for specific downstream applications. So in this work, we try to address this question like by the solution of like generating our own benchmarks for our own use case. So let's say, okay, the user come up with some queries, like the queries in the left side. So the user may have some queries regarding which model to use, or what are those weaknesses of the existing models they have. And then we have like universe of tasks, a huge space of tasks. So that the user can identify this relevant task from this huge space. And then we can generate the concrete task from this space. So that this generated task is relevant to the user queries, and the user can evaluate the model on this query to solve the like original question about the model. Yeah. And finally, you also will get this report to answer the initial queries. So that's the main idea of this, like of our solution. So to achieve this, we build this TaskMe anything system, and now we can dive into it and see how TaskMe anything actually generate a task. So let's say we have this huge task space, and then each dot here is actually a task plan. So we can treat it as a configuration file for a specific task. And based on this configuration file, we have some Python like programs, which we call task generator. And we import this task plan to this task generator, and with some kind of source data or source assets like 3D objects with dense annotations like their category, their color, their attributes, and then we can programmatically generate not only the image or video itself, but also the question and the ground truth answer. So by this simple pipeline, we manage to like generate all kinds of tasks that may like potentially answer user query about specific perspective of the model. So we call this process a more like programmatic benchmark generation. And this system is easy to expand because we can add more and more like source data here. So we can have, so initially we just have like 3,000 objects from Observerse, but we can also add many other like 3D models or other source data into this pool, and we can easily expand the space of the task we can generate. And we can also expand the space by adding more generators. So remember here, each task generator is just a Python program that can generate this image or video and a question and answer. So for example, here, this generator is generating questions related to the materials of the rotating object in a video. And the users can write more new generators, new Python programs. So in order to generate new type of task, like cover some new aspects we didn't cover in our initial version. So this system is very easy to expand. And then we can take a look at what the task space we have in our first version looks like. So in our first version, we have like different visual concepts. So we have more than 300 object categories. So which means those like 3D objects. And we also have more than 600 attributes and more than 300 relationships and many other like basic visual concepts included. And we have 28 task generators, basically 28 like Python programs. And combining all these like basic visual concept and the task generator together, we can generate over 750 million image QA or video QA tasks. So the space looks much larger than existing benchmark that are like collect from the humans or models. So we also have some categorization on the task space. So for example, for image QA, we have like skills like counting, spatial relation, attribute, and object like this kind of recognition capability. So in our first version, we are focusing more on like the perception capability of these multimodal language models. And we have different scenarios. So for example, here, the first scenario, we just copy paste those images of those 3D models into a like white background. And then in second scenario, we just place these 3D models in a real scene, and we render to the image from the scene, so it looks more realistic. And finally, with scene graph and the real images, we can also generate many different questions, and this one will be like all the images are realistic image, are real images actually. And so that's how the like task space look like. And after talking about the system, the kind of task this system can generate, now we're gonna talk about what kind of user queries we can support. So for like traditional static benchmarks, we always like look at the accuracy of model on this benchmark. But with our system, we can answer more questions beyond just accuracy of the model. So for example, we have some like coarse grain user queries here. So for example, which model is best at recognizing planes and which object is GPT-4 bad at recognizing when they're rotating. So these kind of queries, we can use our system to generate relevant tasks for each of these queries and then test the model's performance on a generated benchmark. So that to answer the models like to answer this question or like to select model which is best for different scenarios. So these are just like coarse grain user queries. And we even support more fine grain user queries. Like for example, here, this is a type of top K queries we can support. So basically it says like, what about just find top 5 objects that GPT-4o is worse at recognizing when they are rotating? So this is top K query. And we also have like threshold query, model compare, model debug. Yeah. And but the point is like we have such a huge task space and we cannot like enumerate all the tasks and evaluate one model on millions of tasks, right? So we do have some algorithms that can support like on budget this query result approximation. So the idea here is like we don't need to enumerate all the tasks we can possibly generate, but we just have a budget, like we only want to call a model 100 times, and can we use this 100 model call to resolve some queries we raised at the very beginning? So we have 3 different methods here, like from random to fitting to more active learning like method. So yeah, I won't get into details of this method, but just want to mention here, like we have different strategies, and you guys can check out our paper and there will be more details. And finally, what we have learned with this system, we have done a lot of experiments, and I will only show a couple of results here because the time limit. And so first of all, we compare like different models with a random subset of tasks that our system can possibly generate. And we found like, so first of all, these models are kind of sensitive to the prompt we give, to the structure of the prompt. So we compare 2 types of prompt. One is like more detailed prompt and one is more concise, more succinct prompt. And we find models show different preference to, so different models show different preference to different type of prompt. And we also see some latest model, some latest open source model is already compatible to those closed source model here. And I also show one more interesting result here. So we kind of try to use GPT-4o as an example because at that time GPT-4o is the most advanced closed source model. And we ask some question like, what are the objects that the GPT-4o is bad at recognizing when they are rotating or moving? And here is the results of the report we generate from by evaluating GPT-4o on our generated benchmark. So the thing is here is like, it's actually very interesting because we can see for animals and vehicles, GPT-4 has a relatively good, better performance when these objects are rotating or moving. But for objects like food and furniture and plant, the performance is lower. It actually makes perfect sense because in those videos, like in real world videos, animals and vehicles are moving like all the time. But we rarely see like food or furniture or plant are moving. So that can possibly explain why we observe this performance difference across categories. Yep. Yeah. So finally, as a recap, so task me anything is a user-centric benchmark generation system. We can use that to generate like benchmarks tailored for our specific use case. And we adopt programmatic generation with zero AI model involved. And the space is diverse and easy to expand. Now it can generate over 700 million image or video QA tasks. And we also support different type of user queries and with some on-budget evaluation approximation method. Yep, that's the end of talk. And for more information, please check out our website or our paper. Yeah, thank you.
Awesome. Thanks a lot, Jieyu. So we're at 150, so we can probably allocate maybe 5 minutes for any real-time Q&A. Yeah, so the audience, if you have any question on Task Me Anything, feel free to unmute and ask it here. There's a question on the chat from Nahid. She asks, image QA and video QA, the benchmark being generated with Task Me Anything?
Sorry, can you say it
Yeah,
again?
yeah. If you can take a look at the Zoom chat, you see the...
Let me take a look. Can I just stop sharing first?
Yep.
The benchmark. No, we actually generate many different benchmarks. Like in our paper. So here, image query and video query, just a type of task we can generate. So we can generate both image query and video query. But in the paper, we generate like first of all, we generate like what we call random. So random means we just randomly pick task from the whole space and generate the QA task. So that's a random subset we generate, and we also have some other subset which we call like hard. So the hard subset means we generate task which the SOTA model performs the worst. So by performing the top categories, because we can say, okay, let's return the top 100 tasks that GPT-4 is bad at. And then we can use our system to generate such a benchmark. So image QA and video QA here is just refer the type of task we can generate. Hope that answers the question.
Yep. So I guess like it's a collection of tasks that you generated, which eventually is acting as sort of a new benchmark per se, right? Which is a collection of the tasks you generated with your logic, essentially, right?
Yeah.
Yeah, nice. Thank you.
Yeah, I have a question. What if the user query doesn't exist in your set, in your data set? Yeah, what will happen?
Yeah, right. So right now, the mapping from a user query to the like tasks, list mapping is done by user themselves. It's not automated yet. So the user basically the interface the user see will be a huge like database, a huge CSV like effectively. And like when a user say okay, I want to know what are the objects the model is bad at when they are rotating, and I can just like use normal like database query to query the like rotating and like all object this kind of filtering and filter out like filter this large database and get a subset and use this subset to generate a concrete task. So here the database, I mean the configuration files. So we have millions of configuration. So here, so right now the user have to do this mapping, try to find the configurations that fits the user's need. But that can be done by some like models. So that's one thing. But there's still cases where the user's need that does not like cannot be fulfilled by any of the configuration we can support, right? So yeah, so that's why we make Task Me Anything expandable system. So sometimes when users need cannot be fulfilled, and the user can actually write their own program to generate a task they want. So for example, sometimes the user may want to know objects that are not including our current system, and then the user can just add objects of those 3D objects of those objects they care about to the system. And then we can generate those tasks for them. But sometimes the user may care about some specific task which our system does not support. Then the user have to write their own code to generate that kind of task. But right now, our system try to cover all the like perception tasks as like complete as possible. But for some like high level or like more reasoning type of task, we don't like support right now. Yeah.
Yeah, great. Maybe just like close up this part of the session. Because we in the topic of discussing about the task space, right? So I think when you one of the slide you mentioned that task anything, the task space of task anything can grow exponentially by adding new source of data or adding new task generators. So just out of curiosity, what are the new type of tasks that your team will plan to add on for the next couple of months?
Yeah, so right now, so we are actually working on like extend the idea to like 3D VQA. Like so right now we have image and video, and it can be extend to like point cloud, like model that can do QA over point cloud. That's one thing. And we also and we can also extend to multi-image QA. So that one is much more easier. Yeah.
Great. Yeah. Yeah. So excited to see some of the additional task space being added. Yeah. With that, thanks you for the great talk and opening up the webinar.
Thank you.
And yeah. So Yiqi, you wanna unmute and go ahead with your talk?
Yeah. Let me share my screen. You see my screen?
Yes, I can see it.
Okay, got it. My name is Yiqi, and today I'm going to introduce our work, Motion Graph Unleashed, a novel approach to video prediction. And this work is also accepted by NeurIPS 2024. Okay. So this work is focusing on short-term video prediction. That is, given a very limited number of past frames, the system is required to predict the next few future frames. And so compared to long-term video prediction task, this task setting usually applies to high-resolution videos and emphasized on pixel level accuracy compared to the GT frame. Since the application is usually required on real-time systems, such as online video compression on local device, it has very high requirements on the model size, inference speed, and memory consumption. And to achieve such pixel level accuracy, recent works usually formulate the video prediction or short-term video prediction as a motion prediction problem. So which means it'll predict the future frame by predicting the motion of each pixel in the existing frames. And to do so, the systems need to embed the motion information in the past frames with some kind of motion representation. And several motion representations has already been explored to depict such interframe dynamics, such as image differences and optical flow, which is very traditional, classic. And however, when the dynamic patterns are too complex, especially in some real world video sequence, we have complex situations such as motion blur, and we have objects distortion due to the perspective projection. Those existing motion representation either fall short in the representativeness, or it is not very memory efficient. So to fill this gap, we propose motion graph as a compact and powerful motion representation for a video prediction task. And in the following slides, I will introduce how we construct such motion graph and how we use this motion graph in the video prediction pipeline. So let's take a 2-image sequence as an example. So the input is 2 consecutive frames, and one image encoder would first encode the 2 images into downsample space individually, and each feature patch of the 2 feature maps will be regarded as graph nodes. And then the feature of each graph node will have 2 components. One is the tendency feature relating to the motion patterns of the node, and the other is the location feature, indicating the normalized 2D coordinates of the feature patch in the frame. And for the tendency feature, we calculate a cosine similarity between each feature patch of the first feature map and every feature patch in the next feature map. So, and selecting top K corresponding patches to formulate the dynamic vector set. So we have a K, let me use the laser pointer. So we use, so each of the feature patch will have a K dynamic vector, and we use a point net like operation to aggregate those dynamic vectors into one feature. We call it feature tendency here. And for the location feature, we just use a linear layer to encode the 2D coordinates of the feature patch. And the reason we want this location feature is that you can imagine in a camera, the side of the pixels in the frame will move faster than the pixels in the middle of the frame because of the distortion of the camera. So which means if you want to measure the motion of the pixels, the location matters. So that's why we don't want to lose those information. And here we show the visualization of the tendency feature and location feature after the training. So to give you a better idea about what information those 2 features actually embed. So for the tendency feature, we do a k-means clustering, k = 2. And so the vehicle is moving and the background is static. So we can see when we use the tendency feature to represent the motion of the frame, we can easily distinguish the dynamic part from the static background. So that's for the tendency feature. And for the location feature, we see different part of the frame will have a different value of this location feature. And more interesting, so this image is actually from KITTI dataset. And you may know KITTI dataset is a dual camera system. And when you focus on this point of the visualization, we actually figure out this one is the focus of that camera shooting this image. So which means the location feature kind of reflects the projection pattern of the camera, which is something that we want when we measure the motion of the pixels. And after the node definition, we define 2 types of edge, spatial edge, connecting the nodes within the same frame, and the temporal edge, connecting the nodes in the adjacent frames, which also determined by the top K correspondences introduced in the previous slide. And the reason of those edges is that when we do the motion embedding, we can think of the feature patches that belong to a single object tend to move together. So that's why those nodes are connected. And after defining the edge, we also define the message passing operation. For the spatial edge, we have a spatial message passing, which is implemented by a simple 2D convolution layer, which let the nodes communicate with their direct neighbors. And for the temporal message passing, we implement as a GCN layer to let the nodes in different frames communicate. And build upon the message passing, we define an interaction module. So let the graph nodes fully communicate with each other. And eventually, we will get an updated motion graph, which should comprehensively describe not only the motion of the video, but also the interaction among the nodes. And such updated motion graph then become the motion embedding of the input image sequence. And based on the motion graph, we introduce a video prediction pipeline. We first construct motion graph on multiple feature scales. And after the motion feature learning, we get an updated motion graph. And those downsampled motion feature maps will be upsampled, like super resolution, back to the original image resolution and decoded to become the pixel level dynamic vectors, pointing from the pixels in the historical frames, the input frames, and to the future frames, which is the frame to be predicted. And then we conduct a multi-flow forward warping, so warp those pixels in the historical frames into the future frames to synthesize a new frame. And this pipeline has been evaluated on 3 different data sets, UCF sports containing fast-moving sports scenes, and the Kitty datasets, Cityscapes datasets are widely used datasets covering driving scenes. So they have a different resolution, but they're, I would say they're higher than those long-term video prediction tasks, which we'll use. And we also have a different input, different length of the input frames. And I will just very quickly go through the table. So quantitatively, in one word, we successfully matched the SOTA methods, of course. But more interesting things I want to mention is the qualitative evaluation. So here we show the comparison on UCF sports datasets with MMVP, which is a ICCV 2023 work also published by our team. And we clearly see that motion graph maintains much more image details compared to MMVP. You can see the yellow line here and the shape of the foot of the athlete. And when compared with the optical flow-based methods, we see that motion graph-based methods can handle the video motion under perspective projection better and perform more accurate motion prediction results. Specifically, the first column shows an example of object distortion since the car in the frame is moving towards the camera, and it becomes twice larger than it is in the last observed frame. And our method accurately estimates such motion and also depict those distortion or this enlarged objects better than the optical flow methods. And in the third column, we demonstrate how our method handle another challenge, which is occlusion. So in the last observed frame, the wall behind the cyclists is partially occluded. While in the current frame, or the GT frame, since the cyclist has moved out of the frame, the wall behind it just reappeared. So in our multi-flow forward warping strategy, since we have a multiple dynamic vectors relating to one pixel, so the neighboring pixels can help the system fill the hole, fill this occluded region caused by this occlusion, and give us a better prediction, while the optical flow methods either cannot capture the motion or it generates some artifacts since it cannot get the occluded region to be recovered. And besides the performance, compared to the SOTA methods on different data sets, we all conduct significant reduction of the memory consumption, the GPU memory consumption, and the model size. And I think one reason is that the motion graph is a sparse motion representation, and the operation on which replace heavy convolution layers by much lighter linear layers. So it is a more efficient structure for high resolution videos. And for the future work, we're actually considering using this motion graph as a representation to do other video related applications. For example, we consider motion graph based video generation is, I would say, is a type of long-term video prediction. And we can also make use of this motion representation to do the tracking task. And yeah, that's all for the slides. And let me know if you have any questions.
So thanks, Yiqi. I will let the attendees abilities to ask questions. Yeah, there's one question on the chat. You can see it asking about the tendency feature in your pipeline.
I probably also need to stop sharing to
Yeah,
see
no.
the chat. Okay. Yeah, so the tendency feature is about moving objects. I would say, so when we do the embedding, we don't care if the object is moving or not, because even if static, the tendency feature will connect the same location of the feature patches in the next frame. So the tendency feature can also reflect a static object. But if it's moving, or if it's if those objects are moving in a different way, the tendency feature will be different. Not
Awesome.
sure if I answer your question.
Yeah, thank you.
Great. Is there any more question from the audience? Yeah, so one thing that you mentioned towards the tail end of your talk is around the limitation around inference speed, right? You mentioned it.
Yeah, inference speed, yes.
What are the type of optimization that you think can be improved to?
Yeah, so I think the inference speed, so in our experiments, there are two parts cause the inference speed is cannot be reduced. One is the construction of the graph. So you know, when we want to build the tendency features, we still need to compute the full its cost volume is called cost volume is a 4D matrix, which related to the resolution of the image or the resolution of the feature map. And that requires very heavy computation. So that's one part. And the second part is we have a difference. We have a multiple scales of feature maps to construct the multiple motion graphs. And which means we need to do these things over and over again. But actually, we're considering maybe we can fuse the different scales of features to build just one motion graph to cover all scales, like the all scales of motions, and that'll help us reduce the inference speed. So yeah, that's two headaches for us when we do the experiments.
Yep, that makes a lot of sense.
Yeah, I have a question for work. Do you think this kind of technique can be useful for long form video prediction? Because I feel like this kind of technique is more like some low level kinetics, right?
Yeah. I would say very great question. So we choose short-term video prediction, which is more like a low-level task, to prove that the motion graph can capture the motion of the frames. But when we consider if we want to use this motion representation for a long-term, longer video prediction or even video generation, we will like use this motion graph to generate, I would say, a distribution of the motion. And we sample the motion graph, future motion or motion patterns from this distribution and generates the future videos. So the pipeline would be totally different from the current one, but we tend to use the same representation because I would say it's sort of efficient than off-tail flow and more representative, has a higher representativeness.
Perfect.
Yes, thank you.
Thank you for the question.
Awesome. Yeah, so I think we can conclude the second talk from Yiqi. Really appreciate your time talking over the technical details and answer the question from the audience.
Thank you.
Yeah, with that, Mo, do you want to unmute and go ahead with the final part of the webinar?
Yeah, sure. So I think I should present around 20 minutes.
Yeah, 15, 20 minutes.
Okay, sure.
right
Yeah,
there.
I will give a brief brief talk on my work. So, hi everyone, my name is Mu Cai. I'm a final year PhD candidate from University of Wisconsin, Madison. So the title of my talk today is How Intelligent and Efficient Are Current Multimodal Video Models. So for multimodal video models, it's very specific for models like GPT-4o or for models like open source model like Q1 or Llama Video. So the answer is very straightforward. They are not very intelligent and not efficient. So yeah, that's the conclusion. But let's dig more into a question like why is this happening? So first, I will introduce the data set, TemporalBench. Yeah. So for TemporalBench, it's trying to answer this question, right? What's the nature of question answering? So so everybody knows that current video benchmarks they are problematic, but why? Let's go back to this question. What's the nature of VQA, or what's even the nature of Q&A? The nature is we need to think out very difficult answer or options, right? But current video QA options are either too easy or it's strongly biased. So what I mean by two aspects. One is that there is strong language bias, and second is that there is strong single frame bias. What do I mean by language bias? Language bias means that when you just close your eyes and answer the question by the voice, then you can answer it, right? For example, if I do not show this video to you and ask you who is cooking, right? This question is from a very famous video QA dataset, and the ground truth is someone. Right? If I close your eyes, you can answer a question. Another kind of question is more like a single frame bias. So what do I mean is, for example, if the question is the person is doing what kind of activity, right? Now, if I close your eyes, you cannot answer this question. But if I just give you one frame, you can answer this question. The answer is very simple. It's the man is cooking. So, but we are evaluating videos. We are not evaluating images, or we are not evaluating languages. So the key is that we need to make the temporal dynamics stand out. And let's dig into the reason. The reason why previous benchmarks suffer so much is that the original caption or original description is very coarse-grained. So with the original caption, like the person holding a cup of water then drinks from it, right? From this positive caption, I prompt GPT-4o to generate negative captions where GPT-4o will give me something like from water to juice, from drink from it to throw from it, and from person to kid, right? You can almost solve most of the question from a single frame. Yeah, and in order to solve it, let's just solve the problem from the root. We just discard the original caption and from scratch, right? We put huge efforts to curate a very detailed caption where there are 6 words per second on average. and give such very detailed video caption, we can curate very hard negatives. Such hard negatives can be from right to left, or changes to from left to right, or change from push to pull, and or change the event of orders, like first do something, then do something, or first do that thing, then do this thing. Now the question will become very hard. And the conclusion of our benchmarking is that the best model, GB4O, can achieve 38% accuracy, but human performance is 25% better, or around 30% better than G4O. So what makes our dataset so challenging? The biggest reason is that our dataset is our annotation is very dense, right? Compared to video caption like ActivityNet, Charities, Eagle X, or 40, or Coin, or even let's compare our benchmark with a benchmark coming out with a recent half year, like video MME or Synbatch. We are much denser than that kind of models. That's the reason. That means that once we really build a temporal focus benchmark, the current video question answer models, they'll fail, right? So I will briefly talk about how we curate the caption. Firstly, given a video, we will first let a subset of Amazon Mechanical Turk annotators to annotate the video, and then all the authors of this paper, 15 authors, will refine the caption and produce a very high quality positive caption. And starting from this positive caption, we will leverage language models to generate several negatives by either replacing some words or phrases, or reordering the order of events. So you may ask, why not human during negative curation? We empirically found that the creativity of human is worse than the model, right? This is surprising, but human usually have kind of stereotype when curating the negative captions, and language model can do it much better. But after the language model curating the negatives, we still the authors will still filter to make sure that the quality is the data set is 100% correct, so that it's a reliable benchmark. Yeah, and so how to evaluate the model? The model, given one video, the model need to select, right? Given a positive caption and one of the negative captions, which is the correct caption. Then we do such kind of evaluation in a for loop for all such a kind of replacement and event ordering. So essentially, we are actually doing an image caption evaluation, right? So we are trying to let the model decide which caption is correct for all kind of important places. And essentially, we are building a better caption evaluation pipeline, which is much better than BlueScore or CIDR, which all belong to the N-gram family of evaluation. Yeah. One last thing to say about this benchmark is that we use when you try to use multi-choice question answering, there is a pitfall because now the language model is too smart. If you look at the structure of this positive caption and three negative, the language model will automatically find that the ground truth lying in the first row, and we correct it by multiple binary QA, where we call it MQA, to alleviate this issue. So you can check more details about this phenomena, but the answer is that by using our decentralized evaluation, we can successfully alleviate such kind of pitfall in multi-choice QA. Yeah, that's right. And firstly, for short video QA, we found that with frame going on, with the number of frames increasing, actually the model performance starts saturating, and this behavior is absolutely different from existing benchmarks like video MME, where given more frames, the model performance will increase instead of saturating. So why this is happening? The reason is that our benchmark is not kind of memorization or retrieval-based benchmark where the answer is hidden in a certain frame. But our benchmark is more like the model need to understand the transition between adjacent frames in order to answer this question correctly. So this is the reason why that now, so our benchmark is very short. The videos is very short. It's usually less than 10 seconds, or at most it's 20 seconds for short videos. But the model suffer a lot, and even with 32 frames, there are around 30% gap. Yeah, and let's do some quick detail analysis. The model do well in common video understanding like Tradis, ActivityNet, or Coin, but do a very poor job in fine gene, which is more like a kind of professional video understanding. Yeah, I know 12 Labs also do some football analysis. They will know some kind of generalist video understanding model. They feel short in professional understanding. And also, this is the interesting part. We can further decompose the temporal dynamic question answer into several types, like motion magnitude, motion direction, and we found that the most suffering kind of question is motion frequency. So what motion frequency means that I do something 4 times or 5 times, right? It's actually action counting, and the model really do a poor job in such kind of activity. So it tells us that the video understanding models is not really understanding the videos, especially the transition. Yeah, we also do a long video understanding by concatenating the videos from different short videos. And absolutely, long videos is even worse. So let's solve the short video understanding first. Yeah, and that concludes my first work. So the conclusion is that now we know that given one video and 2 captions, the model suffers. So that essentially is that the large multimodal model suffer at finding the difference between 2 captions, which depicts the subtle difference for temporal dynamics. But we are missing something, right? What about the difference between 2 videos? This is a more interesting question, right? Given 1 caption and 2 videos, can model match which video correspond to the caption? And this leads to our work, Winoground. So before Winoground, let's begin with Winoground, which start with W instead of V. So what Winoground examines is that given 2 images and 2 captions, the model need to match, which of the 2 images match the first caption and which of the caption match the first image, right? This is a funny example, a funny data set, but it actually discloses the nature of matching or the nature of question answering. So we did the same thing for videos. So that's the reason why we changed W to V. And we also do, we again do short video benchmarking, and where the question can be the man eats than watch TV, or the man watch TV than eats than eats. So for each of the captions, there will be 1 corresponding video. And also, like for other kind of questions like object viewpoint, spatial transformations, we also have corresponding question like water turning into ice or ice turning into water, right? Here is an example for action, where we have 2 videos corresponding with the captions. So at inference time, what you can do is that firstly for text score, right? This is a typical VQA setting. Given 1 video and 2 captions, 1 is correct, 1 is incorrect. The model need to answer which caption correspond to the video. So this is a traditional video question answer evaluation. But here is something new, right? Given 2 videos, which video correspond to the caption? This is a very interesting academia and practical question to answer. So this is we found that this is a much harder question than the previous one, which we call text score, where the model need to distinguish the difference between two captions. So we collect we collect 7 types of video understanding types, including object, action, viewpoint, interaction, cyclical, spatial, and contextual. You can find more details in our website. Due to the limited time, I would directly jump to the conclusion. The conclusion is that again, this benchmark is very easy for human, right? Human achieve nearly 100% accuracy, but the model suffer a lot. There is also 30 to 40% performance gap. So yeah, this is very interesting, right? For 2 benchmarks developed by our groups, by our groups, they both show around 30 to 30 from 30 to 40 performance gap, which shows that the current video understanding models are really sucks. They are really bad. But more interesting thing is that you will find that for video score and text score, all models lie in the lower half of the figure, right? Which means that the model is better at distinguish the difference between text instead of image instead of videos, which means that the vision-centric multimodal understanding is still something far away. We still can't figure out a way to solve this problem. Yeah, and you also find that for clip style model like video clips, they are very bad because of the very short embedding size. It cannot cover the temporal dynamics. That's for sure what's happening. Yeah, that's all. So what's lacking? And the model are better at understanding languages instead of the video information. And the model now, the sample frames, which shouldn't be a good choice, right? We truly need a video understanding model instead of relying on single frames. And another other challenges, they also exist. Finally, I will introduce one work that we try to solve this kind of problem partially. So for videos, it's composed by a lot of frames, right? The bottleneck of current multimodal large language models is that there are too many tokens. They make the system very inefficient, and they can even distract the large multimodal models from focusing on useful information. This is a huge problem for high resolution images, and especially for videos. It can be millions of tokens. So for example, for current open source models, Lava 1 Vision, there are 6,000 tokens for 32 frames. For video Lava and IGVL, which are early works, they all have 2,000 to 3,000 tokens to represent 6 or 8 frames. But we all know that token is money. If you have too many tokens, this will be a really huge budget for your company and for your lab. But the thing is that for image complexity, it varies between the image complexity. It depends on the image itself, right? If you look at the image on the left side, you may just need 1 token or 2 tokens to represent it. But if you look at the bit rate on the right side, you may need hundreds of tokens to represent it. So that's kind of an input-dependent problem. So then the next question is, can we develop a system that can represent the image or video with the arbitrary number of tokens? And this is the idea and motivation of my final presentation, my final project. So with Matryosha representation from the name, you can guess that now we represent the video information in a nested manner, where for one image, we can represent it with 1 token, 9 tokens, 36 tokens, all the way until 576 tokens. And our technique is extremely simple. We gradually do average pooling to get a smaller set of video tokens. And we empirically found that this simple approach works better than more complex approaches like Q-former resampler or something else. So at the end of the day, we can achieve some functionality like this. So when we ask the question, describe the image for me, from fewer tokens to more tokens, the model can gradually increase the detail and give you a more correct, give you a more fine-grained answer. And we found that after training in this way, right, trained with multi-scale visual tokens, now the multimodal system becomes very efficient. For example, in Batch, which is a comprehensive image understanding benchmark, now with one token, right, the performance drop is only 5 to 6%. But with 36 tokens, the performance is just 1% worse than the full tokens. We further evaluate on videos, where compared to baseline like Lava Next 7B for video understanding, we achieve similar performance using 1.6% of visual tokens. One more intriguing thing is that you will find out that with 720 tokens, the performance overall is better than 3,000 tokens, which again supports our hypothesis that more tokens is not always better. You should really represent your visual information using a compact representation space instead of wasting the number of tokens and wasting your money on this. And a side effect, a good side effect of our approach is that now we can somehow provide a way to evaluate the complexity of images. How to do this? For a visual question answering case, we can collect the correct or wrong response, right? And we found that when all sets of tokens cannot answer a question correctly, the question is very hard, right? The text here is very small. But for the easy questions where all scales can answer it correctly, the text is usually very large. So this essentially provides a way similar to autoencoding to determine the difficulty of the image or the image along with question. Yeah, that marks the end of my presentation. So in conclusion, today's video understanding models are far from human intelligence, either from efficacy or from the angle of efficiency. All code, model, and data are available. Yeah, thanks. If there are any questions, I'm happy to answer.
Awesome. Yeah, thanks, Mu.
Yeah, I will go through the questions in the chat one by one. So
there's not a lot of question. I think it was mostly talking about the quality of the talk.
Yeah. For first comment, so since the counter VLMs are not trained with detail capture, they are not so good. Yeah, that's correct. And this is actually one of the most important directions people now are focusing on. There is a work called MOMO from AI2, where they try to use very detailed captions to train an image understanding model, and they show amazing results. So this kind of work kind of demonstrates your point.
Yep.
Yeah.
Okay. Sounds good. Yeah, I think we 2:40, so we 10 minutes over time, but I guess we can close up the webinar right now. Thanks again all the speakers for taking the time today to present your work. Yeah, just some quick just note. I think I'll try to publish the recording of the session by early next week. So once one is available, I will notify the speakers as well as the attendees and when that become available, and you can view it on your own time. And yeah, we run this session on a weekly basis. So be on the lookout for details for upcoming session and upcoming speakers if you found informative. Yeah, thanks again for making time today, and appreciate the time. Hope you guys have the rest of your Friday. Enjoy your weekend. Cheers.